So welcome to Physics 4411 or 9411, which is the PhD variant. We are not going to make any distinction between the two variants. So essentially the project will be the same. After some introductory words, we could have some introduction about each other. I know there's people online, but we could take during the break. We could just introduce ourselves a little bit more. And what I want to do now is just to give you a quick overview of teaching material and say a little bit about the motivation behind the course and a little bit about the lab sessions. So you've probably seen from the schedule, and this is the official website of the university. So there are three different channels of information. One is Canvas, which is a closed environment. And then there is obviously this one, which is fully open and where you will also find the schedule. And for those of you who may not be too familiar with the University of Oslo, there is actually the possibility to subscribe to these activities, which means that you will get a warning or a message, a text or an email in case there are changes. So there is an error in the schedule here that it actually appears 2 times. But since we have lab at 12, it's much better to have the lectures from 10:15 to 12, and then we move to the lab sessions afterwards. So the lab is in another room, which is actually this physics 434, which is in the 4th floor in the physics building. But we will keep the lectures from 10 to 12, and then we proceed with lab sessions. And hopefully this room may be available so we can stay in the same place all the time. But I will let you know if that is the case. But there is no session from 8 to 10. Okay, so this is the standard, the plain website of the university. And if you then click on this semester, you will see down here messages. These messages will also appear on the Canvas site. So we will have a kind of duplication, actually triplication, because you will get the same message by email every week. So I normally send a kind of a weekly update with plans for the coming week. So you will find the messages there. And then there's also a GitHub address where you will find all the relevant information for the course. And that's where we have all the educational material. So Canvas, you will find that pretty similar to what we have here. So if we now go to the courses here and look at this one, you will find typically the announcements, and these are the same messages and which you will find on the official website. And if there are changes, I will send you an email. So anyway, there will be a weekly email at the beginning of the week about the plans for the week to come. Now, the GitHub address is actually perhaps the most important thing. And this is where you will find all the teaching material. So I assume that everybody is more or less familiar with version control software like Git and repositories like GitHub, GitLab, etc. And you can then clone all the material to your laptop. If you want to use that as your own material, I normally recommend fork it, because then you can use that as your own teaching material and then update it to GitHub. Alternatively, if you just clone it and then do a weekly fresh up, you will always get my weekly updates, because I typically find errors, I make additions, so I typically make a weekly update during the weekend. So it's up to you on how you want to use the material here. And in the material, what you will find when you in the beginning here, there's just a plain README. So Ruben is the other person who is helping us with the lab sessions. And but Ruben is away this week because he's running experiments at CERN. So he's an experimentalist, and sometimes they have to be at CERN. The GitHub address here in a doc folder, if you go to Pub, you will find all the weekly material. So we are in the first week, and that's where you will find the teaching material either as a PDF or Jupyter Notebook. So when I typically teacher will normally switch often between a PDF file and the Jupyter Notebook, because sometimes I run codes. Now, when it comes to programming language, you should feel free to use the one you prefer, but we typically offer assistance in C++ and in Python. So if you wish to write everything in Python, you can do so. We have actually 2 templates, which I will discuss a little bit today, in both C++ and Python for the first project. The other possibilities, if you are coding in Julia, we can roughly assist you. And then if some of you are more familiar with Fortran, which is also much used in scientific computing, then this is also language which you should feel free to use. Some people have written everything in Rust. I am not that familiar with Rust, so that means you would be more on your own. But we normally leave that as something to you guys to actually decide which programming language you feel is the one which makes you most efficient. Okay, so this is roughly about the material. You will find the project. So the first project, if you now go into 2025, we are coming back to that later in the lecture. So you will find the PDF file. And here you will also find a LaTeX file if you want to use that one for writing the report. So the project is something we want you to write as a scientific report. So you will see through the project that you have different exercises. That is actually to baby step you through the different elements which are needed in the project. But then when you write your answers, we want you to write them as you would write a scientific article or a scientific report, or just a report. I mean, they have essentially the same structure with an abstract, an introduction, theory sections, results, conclusions, discussions, and then references, etc. So this is also something which helps many people in setting up the basic framework when they're writing either their PhD, their first scientific article, or their master thesis. Okay, so that's where you will find the projects, which we will go through during the semester. What I'm going to do now is to switch over to the slides for today, and you probably have access to them, so you will always get access to the teaching material in good time before we start. But let's now take a look at the slides here. And as I said, I'm going to switch a little bit back and forth between the slides and the Jupyter Notebook. So the topic today, as we said, is an introduction, an overview of the topics which we want to cover. And I will have to explain a little bit why we focus on Monte Carlo methods and why this is a useful method, why it's important. As I said, C++ and Python are typically the programming languages which we will present in the lectures. So in many of the examples which you will find in the lecture notes, I have written the codes in a very simple way, and I use Python. And one of the reasons for that is that allows me to run things in the lectures easily and then visualize. So there's a pedagogical element in why the codes you will find here are in Python, but you will also have access to a framework in C++. So this is something which we also can discuss a little bit more in detail. I mean, what kind of programming language you want to emphasize. So the teaching material is going to be given in terms of videos we will present. You will have the lecture notes and also reading assignments, and additional background from the 2 textbooks which we have here. So this is, so essentially you have the material which we are watching now is this one. But then let me just bring up the 2 textbooks. So there is one which you can access freely from the University of Oslo. What I've done is to collect every chapter into a single PDF file, which you can access from the Google Doc here. Now, this book of Hammond and Lester and Reynolds is out of print. And if you want to buy it used or via Amazon, it's very expensive. and it's not worth it. So there is a PDF version. I don't know how that landed here, but it just landed there. So feel free to use that one. So in this Google Drive, so this book here is something you can download if you're on an IP address from the university library. Are you familiar with how you use the university library? So there is a website which is called Aurea. Now let me just show you that one, because that's something which is useful to have seen. And because the university actually pays a lot for these different subscriptions. So if you go to this website, aurea.no, then here you can search. And sometimes when you search for textbooks, you will also see that it is available online. So the textbooks by a publisher like Springer are fully available. So you can download them for free, the full PDF. Cambridge, as a publisher, they actually give you chapter by chapter, which sometimes is a bit annoying, but you can download all the chapters. And what I did was actually to bring them together in just one document. So that's the one you find on the Google Doc. So this is the website, and you would then have to log in with your UIO identity. And then from that one, you can actually download everything. So this is something which is highly recommended. So let's just go back to the slides here. So these are the two textbooks which I will follow, and I will typically give reading suggestions from chapters or sections from these two books. There is always a problem with many of these textbooks, is that they try to sometimes to how to say, some of the textbook may sometimes be more advanced and have less mathematics. So hopefully the lectures are meant as a way to bridge the gap between the textbooks. So there is no kind of ideal textbook here. Now, the thing I wanted to point to, actually two templates for the first project, which you then can reuse in the second project. And there's a C++ template, fully object-oriented. And for those of you using Python, I mean, JAX has become a kind of standard library with Python, which is used both for taking numerical derivatives. So a project like automatic differentiation is included with JAX. It has just-in-time compilation, so it gives you normally a much more efficient code. So we made two templates here, which you may find useful for the projects. So these are the textbooks, and as you saw, the lectures are Fridays from 10 to 15 to 12, and the last session is going to be May 16, and the same with the lab sessions. You will typically get an email. I was thinking of having the first project at a deadline for March 21st, and then we move on to the second project with a deadline June 1st. There is no exam in this course, it's only project work. So that's something which I prefer. I'm very much fond of project-based teaching. So we have two compulsory projects, only electronic reports, so you will hand it in Canvas. And there is also a guideline in the GitHub repository on how to write a scientific report. But these are also things which we normally encourage you to discuss during the lab sessions. The lab is at 434 in the physics building. And these are typically programming languages which people have been using during the different semesters we've been running at. So now you may ask, why Monte Carlo methods? What's the why do we present those? There are several reasons for that. Stochastic methods are extremely important in science. So that means knowledge of statistics and probability theory is normally a very good entry point. When you're evaluating integrals, when you have a high dimensional integral, it's normally solved by stochastic integration. So what you will see is that this variational Monte Carlo method is a method where you, in principle, you are going to evaluate a multidimensional integral by stochastic sampling of the points you need to integrate over, the domain of points. Now, Monte Carlo methods also have an advantage, because many people who enter this course may have forgotten some of the quantum mechanics, or you may have not have taken the formal first course in quantum mechanics. So in university here, this corresponds to Physics 3.110. So Monte Carlo methods have a lower threshold for getting started. Many of the many-body methods, which are used to solve quantum mechanical problems, are often based on differential equations or rewriting of the equations in terms of Green's functions, etc., etc. So there are different methods. In quantum mechanics and what we normally call few-body and many-body physics, you will encounter methods like partial differential equation solvers, which are useful for low-dimensional problems with few particles. If you move to, so that means a differential equation solver, you can rewrite everything as an eigenvalue problem. That means you have something which is called a Hamiltonian matrix you diagonalize, and then you get the eigenvalues and the eigenvectors. This is often limited because the dimensionalities of the matrices you can diagonalize quickly reach what is the computational limit. So nowadays, that means matrices of the size of 10 billions times 10 billions are the typical dimensionalities in eigenvalue problems. Then we have many other ways of rewriting the equations. So we can rewrite it in terms of a matrix inversion type of problem. So mathematically, this leads to essentially specific recipes. So you have diagonalization, which in physics and chemistry is called full configuration interaction theory. If I invert the Hamiltonian, then this gives rise to Green's function theory. I can rewrite Schrödinger's equation or Dirac's equation if you're doing relativistic physics as a set of coupled nonlinear equations. That leads to methods in quantum chemistry called copper cluster theory and many other types of methods. You can do Taylor expansions, which leads to perturbation theory, where you actually Taylor expand around a specific energy. And you have many other mathematical algorithms which lead to different many-body methods. So Monte Carlo methods, in addition to us getting acquainted with important methods like Monte Carlo methods, which are using in many, many disciplines in science, from finance to life science, geoscience, and so on, when you have large dimensionalities, they are also methods which have a lower threshold for getting started. So in the beginning, you may not see that, but my hope is that I will convince you that Monte Carlo methods will allow you to actually solve complicated problems with less mathematics than you would have with other types of methods. So what we want you is to be able to simulate many quantum mechanical systems with many interacting particles. And these methods are used in a broad spectrum of scientific applications, essentially all scientific fields you may encounter. So I am assuming that you guys are either quantum chemists or physicists. Is that correct? So that means that some of you will probably use these methods in your thesis work. And clearly, we want you to learn to structure larger projects with unit tests, object orientation, and how to write clean code. These are things we will discuss at the lab sessions. And then there's also an element like a statistical interpretation of the data, because now we're going to use Monte Carlo methods, which means that we are going to calculate a statistical expectation value. But since we cannot have an infinity of what we call samples, that means that there will be an error. And how we analyze the errors and how we treat that is part of what we call the statistical analysis of data sets. And that's something which many of you have probably encountered in other occasions as well. But this is something which we also need to deal with. Now, another thing which we need to look at, because at the end, we are going to have a theory where the integral which we calculate is going to be given in terms of a set of parameters. And then we want to find, in the case of the energy, the minimum as a function of these parameters. And that leads to optimization problem. So for those of you who are familiar with fields like machine learning, it's actually the same type of optimization strategy which is used here. So you have a function which depends on many variables. This function, which is the energy, the expectation value of the energy, is a convex function, and we want the minima of that function. So that means that we're also going to look at how we can optimize a multi-dimensional object. So if you're familiar with machine learning algorithms, you will probably remember Newton's method, which is normally the starting point for finding the minimum or the roots of a function. Then we have a parallelization and code optimization. And if we look at the second project, we've actually tried to be very open there because we would like to design that so that it gets closer to your research interests. So we're actually proposing different paths. Now, I know that some of you are taking the course on machine learning, or if somebody's also taking the course I teach on quantum computing, there is a possibility to link the second project with the other courses. So that saves some efforts because there are topics which are similar. So we are going to deal also with standard parallelization. I don't know how familiar you are. We have an excellent course at the University of Oslo, which is called IN 4200. There is a bachelor level variant of it, 3200. But we will cover some of these algorithms here. We are going to look at algorithms for Monte Carlo simulations. And that means that we have to encounter Markov chains, the Metropolis algorithm. I guess not everybody's familiar with the Metropolis algorithm. This is a central algorithm in the simulations of statistical systems. And together with the Metropolis Hastings, these are ways which we are going to, these are algorithms which we will include. In particular, we're going to focus on something which is called importance sampling, which are normally lead to what we call improved Monte Carlo methods. Then we have statistical analysis of the data. We're going to look at eigenvalue solvers. Now for project 2, the first project deals with a system of bosons. Now there's several reasons for that system of bosons. One is that the system allows you to simulate the type of Bose-Einstein condensation, which has led to a series of Nobel Prizes in the beginning of this millennium. So bosonic systems where you have a condensation, which means that you have a macroscopic phenomena where all the particles have the same essentially velocity. And this is a system which is normally cooled down to a certain temperature, and then it undergoes a phase transition from a normal, what we call quantum liquid of bosons, to a system where all the particles have the same velocities. So this is done experimentally in a very ingenious way. So you can, the way you would do it, you would trap bosons. So this could be atoms which have a total spin, which is an integer. So the helium atom, for instance, is a boson. It behaves like one if you just treat it as an atom and leave out the electrons and the protons' degrees of freedom and just think of that one as one entity. That has total spin equal to 0, and it behaves like a boson. That means particles with integer spins. Now, these systems are actually cooled down to very low temperatures. So if you think of a gas of these particles, which are then trapped in a so-called ion trap or Penning trap, that was a Nobel Prize in Physics in '89. And these trapping techniques, essentially what they do is that you can create electric quadrupole fields, which look like a harmonic oscillator. And then you can trap particles in small regions in space. Then these particles have a velocity distribution, which looks like a Boltzmann-Maxwell distribution for the velocities. And by laser cooling, which means that you hit those particles which have the highest velocities in the tails, then you can slow down the bosons so that your velocity distribution becomes more and more peaked. And at the end, all the particles would have the same velocity. And that is a phase transition where you have a system, a microscopic system, where all the particles have different velocities, and they're being cooled down by laser cooling to a point where all the particles have the same velocity. And then your gas behaves as a macroscopic entity with the same velocity. And that's called the Bose-Einstein condensation, which led to a series of 4 or 5 Nobel Prizes in theory and experiment in the beginning of this millennium. So it's been and still is a very hot field in physics. It has also had important consequences because all these techniques where you trap particles are now being used for making candidate systems or platforms for quantum computing. So in quantum computing, you rely totally on your capability of isolating single particles whose states you can manipulate. So the second project then, there are several variants. And one of the variants builds on the first project. But instead of looking at the bosonic systems, you can then look at fermionic systems. So that means ensembles of half-integer particles. That means that you need to change what we call the trial wave function to one which is symmetric to one which is anti-symmetric. And these are technicalities, but essentially the first project there means that you can actually move on rather quickly and just change the physical system. Now, the second variant is tailored to more people from quantum chemistry, but also people who are interested in the study of the time evolution of systems. And that's important if you're looking at collisions between particles, but also if you're looking at how a system reacts to, let's say, a laser pulse. So if you're more into quantum chemistry, 2 and 3 are typical projects which have been chosen by people doing that. There's also the possibility to solve the same system as in project 1 using machine learning methods. So for those of you taking physics 5429 in parallel, there's a possibility of actually merging the projects in that course with this one. And the other things are eigenvalue problems with deep learning methods, but we have also had the option of looking at some quantum computing and quantum machine learning projects. So we leave often a lot of flexibility and tailor the last project to people's scientific interest. And we normally encourage people to collaborate. So you can hand in a common report if you want to set up a group, and then you can just keep collaborating that way. I mean, we don't force people to collaborate, but it's often very beneficial because one of you may be very good in mathematics, the other one may be good in computing, the other one is like me, who's good in making coffee and cracking lame jokes. Okay, so if we are now looking at the topics which we're looking after, so we are going to look at methods for finding minima in multidimensional spaces. We are going to look, if you look at project 2, there's a possibility of studying iterative methods for nonlinear equations. Obviously, object orientation is something which makes life much, much easier. And these are things we will discuss at the lab session. Data analysis and resampling techniques are very important parts of a statistical analysis of the data. So some of you may have heard in statistics courses something called the bootstrap method. If you're taking a course in machine learning, you may have heard of other methods like the jackknife or cross-validation. These are ways to resample your data sets. Here we are going to also introduce another method which is useful when you have lots of data, which is the case here. And that is called the blocking method, which allows you to find a precise estimate of the error in your calculations. So one thing with Monte Carlo calculations is that you will provide an expectation value. That's what you will calculate. But then your expectation value, since this is a statistical method, a stochastic method, you need to provide a standard deviation. And to be able to evaluate that properly is actually an art by itself. And that leads to this technique of resampling methods. And then we are going to look at physical systems, which are relevant also for the research of perhaps many of you. So We are going to look at simulation of trapped ozons, and that's through Monte Carlo methods. And then you can now see the different projects which we have discussed. I actually mentioned a lot of it already. You can actually reuse the same system, and this is something which then can be linked with the Physics 5429 if you're taking that course. This became a little bit dense here, so let me just switch. Sometimes the LaTeX slides are not optimal, but let me bring up the Jupyter notebook here, because I wanted to show you this equation here, because that gives you a little bit of the motivation for the Monte Carlo methods, or the quantum Monte Carlo methods. So the basis for these Monte Carlo methods is you calculating a quantum mechanical expectation value. And that quantum mechanical expectation value is in general a multidimensional integral. So if you want to calculate that integral, if you think of atomic neon, so atomic neon has 10 electrons if you freeze out the proton degrees of freedom and the neutrons, and you only look at the electronic degrees of freedom. So you have 10 electrons in 3 dimensions. So that means that that integral for atomic neon is a 30-dimensional integral. And if you think of classical methods like the trapezoidal rule or Gaussian quadrature, which are the standard methods for low-dimensional integrals, there is no way you can calculate that in a decent amount of time. So if you think of this being a 30-dimensional integral, it means that the number of operations you will need to do, if you now have 10 particles, and you take, suppose you take 10 particles in 3 dimensions, and in every direction, X, Y, and Z for each particle, you put in 10 points, 10 integration points, because you will always discretize. Now with 10 integration points, you have 10 to the 30th evaluations which you need to do. So if you then think of doing this in a very brute force way, and that every evaluation takes roughly 1 floating point operation. I mean, additions and subtractions are roughly like that, but multiplications and divisions require more. But let's assume that every operation you do is counted as 1 floating point operation. So if you have to do 10 to the 30th floating point operation, and you have a machine like my laptop, which is pretty decent, and can do, let's say, 10 to the 10th operations per second, you will still have 10 to the 20th seconds, which you need in order to evaluate an integral with only 10 points in each direction. Now, for the neon atom, this would give you a pretty poor result with 10 integration points. You would need at least between 100 to 1,000 when you integrate in the X, Y, Z direction to get a result which you would be happy with to, let's say, 4 or 5 decimals precision. Now, if you do, if you have, let's say, a machine which gives you like something like a frequency of 10 gigahertz, or let's say now that you're more ambitious and you get a petaflop machine, so that means you can do 10 to the 15th operation per second, you still need 10 to the 15th seconds. Does anyone here remember the lifetime of the universe, the estimated one, in terms of seconds? What's that? That's a good number to think of, because that's as close as to infinity humans can think of. I mean, life is so short. Yeah. Yeah, you've probably seen the number. I think it's 10 to the 17th. So if you have a petaflop machine, and you can do 10 to the 15th operations per second, and you want to do 10 to the 30th, then you still need 10 to the 15 seconds. So you're getting close to the age of the universe in order to perform a pretty bad calculation. So Monte Carlo methods are actually those methods which help us when we need to evaluate these big integrals. There's another benefit with Monte Carlo integrations, is that the error stays the same, irrespective of dimensionality. And the error is proportional to 1 over the square root of number of samples you do. So a sample means you picking a selection of these points randomly. So this has to be evaluated statistically, which means that the points you pick here are evaluated in a random way. So we need random number generators to initialize the system. So one sample is one random selection of R1 up to Rn in the X, Y, and Z directions. So that means that if you do 1 million samples, then you have chosen 1 million set of such positions in space. And then you evaluate the integral. So what you're hoping for then is actually that you, by doing, let's say, 1 million or more than that, are getting a good description of that expectation value. So I'm trying to give you some of the basic motivations here for the course. So let's go back a little bit to the slides here again, because I wanted to discuss other things. So you can rephrase, just understand the dimensionality. This is an example from nuclear physics. If you want to rewrite everything in terms of differential equations, you can always rewrite a second order differential equation in the position space in terms of coupled first order differential equations. So if you take a nucleus, which has a given number of neutrons and a given number of protons, then if you have a nucleus like beryllium-10, which has 4 protons and 6 neutrons, that gives you roughly 200,000 coupled second order differential equation. And that's quite a challenging problem to solve. And that tells you why Monte Carlo methods come to our rescue when the dimensionality becomes so big. So I mentioned in the beginning different types of many-body and few-body methods, which you will find in the literature if you're familiar with many-body methods. So Monte Carlo methods are some of the favorite ones. We have large-scale diagonalizations, which means that we use an iterative solver. If the matrix is symmetric, this is called Langs's algorithm. And the typical dimensionalities which people tackle are matrices of dimension 10 to the 10th times 10 to the 10th. But you are solving this iteratively, so you're building up the full Hamiltonian matrix by iterations. And this is a method which converges to the lowest lying states and the highest lying states. So if you need many states in the middle, then this method is not very efficient. Then we have copper cluster theory, perturbative many-body methods, etc., etc. And often the physics of the systems hint at which many-body methods to use. Now, Monte Carlo methods are well tailored to study the ground state of a system. So what you typically will get is the lowest state of the system because it uses the variational theorem. So that means that with a given ansatz for your trial wave function, you will get a result which abides to the variational principle, which we are coming back to pretty soon now. Now, there are many pros and cons. So I think and I'm going to try to convince you that it is physically intuitive. You can think of like that integral which I mentioned, like these electrons jumping around in space in different positions, and that then you're sampling all the possible positions the electrons can be in, and that your final integral is then just a sum of all these samples. You will see that it's not that difficult to implement, and I will show you a code example at the end of the lecture today on how you can implement it. And that code example can form a kind of backbone for you getting started with a project. So this is one of my claims, actually. And the diffusion Monte Carlo, which is done on top of a variational Monte Carlo method. So this is also a variant for the second project. Diffusion Monte Carlo allows you, if you can simulate long enough, you can actually show that mathematically. It can give you the exact solution to the ground state of a problem. But in order to perform these simulations, you need a good guess. And that good guess comes normally from a variational calculation. So the variational calculation we are going to calculate will always have a lower limit, which may not be the exact energy for that specific system. but it will provide you with a limit. So diffusion Monte Carlo calculation is actually you transforming Schrödinger's equation into a diffusion equation in complex time. So Schrödinger equation has a complex term, an imaginary I, in front of the time part, the first derivative. Now, this part is then rotated into the complex plane, and then you get a complex time without the imaginary term, and that looks like a diffusion equation. So that's why it's called diffusion Monte Carlo. And you can actually prove mathematically that this converges, if you simulate long enough, to the exact ground state energy. However, for the simulation to run correctly, you need a good guess, because else you're random walker. So in this case, in all these Monte Carlo simulations, you can think of the system being described by a set of random walkers, which sample all possible positions in space. So a PDF, when I use that as a word here, that stands for a probability density function. So that's essentially the probability which we are going to use. Sometimes I will just call it the probability, or just the probability function. So the solution has a statistical error, which can be large. And there's also a limit to how large systems one can study, because you need often a huge number of random walkers. So it's not so that what I'm saying now that Monte Carlo methods can give you exact results. This is very nice, but all these methods have their bottlenecks. And in this course, we want you to appreciate and understand where the bottlenecks are, because then knowing the pros and cons means that you can point to places where you can develop the theory further. Yeah, we're getting close to the end. You can actually read many of these applications. So these are typically application of Monte Carlo methods. So one reason why we use Monte Carlo methods here, as I said, is not only because they're widely used in science, and this kind of statistical approach is extremely useful. If some of you ends up in finance, you will actually end up doing Monte Carlo calculations. I actually had a very good friend who did his PhD thesis on Monte Carlo samplings, and he ended up in banking, in a bank which had I think he had one of his first jobs in Monte Carlo. So Monte Carlo, actually the name Monte Carlo comes from the casino. Okay, so these are the type of applications. So what I wanted to do now after the break is actually to say a little bit about the basic philosophy, just to give you the overarching view on Monte Carlo methods. And I'm going to show you a Jupyter notebook, a code, which you can use as a kind of framework for getting started with Monte Carlo calculations. So the next lecture, I want you to give you the kind of, I would say, the overarching view. And then we're going to dive into the details next week and so on Markov chains, the mathematics behind them. We're going to derive the Metropolis algorithm and all these sampling rules, which are widely used when you do, let's say, a statistical approach. If somebody here has done research or studied statistics and Bayesian statistics, has anyone done that? There you will also encounter the Metropolis sampling and Monte Carlo sampling, because that has actually allowed a field like Bayesian statistics to really enter much, much larger dimensionalities and explore other probabilities. And there you will also encounter other things like Gibbs sampling, which is also another way to accept whether you can move or not. So when you run these Monte Carlo calculations, you're going to propose a set of positions. And with that, you will calculate a contribution to the energy, which means this integral, which you see there. And then you're going to propose a new position. And then you can decide to accept flatly all suggestions, or you can have a rule to accept it. And this rule is the Metropolis algorithm. So the Monte Carlo machinery is the overarching algorithm. But then when you are suggesting moves in space, then you need a way to say that I accept this move or I reject it. And that is the Metropolis algorithm, which is one of the central algorithms in accepting. And it's so popular because it's so simple. So everything which is simple becomes popular. So you're probably familiar with if you've done machine learning, there is a way to correct the calculation of gradients, and it's called an algorithm which is called ADAM, adaptive momentum. That algorithm is very simple, but it has more than 200,000 citations since 2014. So if you make something simple, people will use it. And the Metropolis algorithm is extremely simple. So the thing before we take a small break, which I wanted to say now, if you look at this integral, what we are going to do after the break is to introduce a trial wave function. So this is our guess on the wave function, this psi of t. And in our case, we are going to be guided by the physics of the problem. So from Schrödinger's equation, you can extract some minimal mathematical properties which the solution needs to have. And then with that, so this t, psi of t, is going to depend on a specific set of parameters. And that's where the optimization comes in. And then it's a signal that we should stop now. Now let's continue after. Let's take a small break, and during the break we can also try to get to know each other a little bit better. So what we are going to do now is to try to look at some of the mathematical details of Monte Carlo calculations. So let me give you the kind of overarching things first. So the integral which we will evaluate is an integral given in terms of a trial wave function. That is our ansatz or guess for the wave function. And with that one, we are going to evaluate this integral. And then there's something which is called the variational principle, which tells us if E0 is the exact answer for the ground state, then this trial wave function can give us, if we have the exact answer, obviously the exact answer, because if you have the exact answer, H, the Hamiltonian, acting on psi, gives just a constant, the energy times psi. And if psi is normalized properly, then the numerator becomes just the energy, a constant, times a norm, divided by the same norm. And that means that we have the exact result. But in general, well, I should say, if we have the exact wave function, there is no point in doing this calculation here because we have solved the problem. So we are going to try different wave functions, and the standard procedure in a variational Monte Carlo approach is to try different wave functions, and then you would pick the one which gives the lowest energy and the lowest variance. So when you run calculations with a Monte Carlo method, you don't know whether you have a good energy or not. So you're just getting a number which will follow the variational principle. Now, when you have that, then you can ask yourself, is there a measure of whether I have a good representation of the wave function or not? Now, we will see later that mathematically, there is a quantity which has an exact value, and that is the variance. And the variance of the energy, if you have the exact wave function, is exactly equal to 0. So many people make the variation on both the variance and the energy. We are going to see that in examples. But what I want to do now is more to give you a kind of quick reminder on the variational theorem. So let's switch from the slides and go over to the whiteboard. So let me just change quickly here. So the variational theorem is actually very easy to prove. And what we will need in a variational Monte Carlo calculation, one important ingredient is this psi-t, which I'm now going to phrase in terms of the parameters which are going to enter. So this psi of t here is going to be a function of the positions of the particles. So R, uppercase R, is now a container for all the positions. So let's just write it down here. So this R is now a vector which contains the positions of particle 1. So this is a kind of funny letter, is actually my best attempt at making the letter R. Have me excused here. And this goes up to all the particles which we have present in the system. So I'm going to use uppercase N here as the number of particles in the system. So this uppercase R is now a container for all the positions which we have. And then we can be in 1 dimension, 2 dimensions, and 3 dimensions. So the project which we have, we can solve that, project 1, in order to get started for harmonic oscillator. We are going to look at the harmonic oscillator in 1, 2, and 3 dimensions. And if we don't have any interactions between the particles, then we have an exact answer for the harmonic oscillator. And that is extremely beneficial because when we develop the codes, we have something we can benchmark our code against. Now, in addition here, I'm going to have a set of parameters. So here I'm just going to call it theta. I think in the lecture notes I used alpha. So this theta is the set of parameters which we have, not that one. So this could be a set of parameters, which could be a theta 1, theta 2, etc., up to some theta m. So these are the parameters of the wave function. And these are the parameters we want to optimize. So we are going to calculate now an expectation value of the energy as a function of these parameters. So what this means for us is that if we now use the standard quantum mechanical, and this is a starting point, the standard quantum mechanical expectation value, what we are going to calculate then is the expectation value of the energy as a function of these parameters theta. And if we then go into any textbook in quantum mechanics, this is now going to be given by this multi-dimensional integral. And then we're going to have the wave function of R and theta, complex conjugate. And then we have H, and this is the Hamiltonian, which typically depends only on the positions, but also it can depend on other quantum numbers, like spin and so on. We are going to look at the Hamiltonian, which is spin independent. So we are going to leave out the spin degrees of freedom. There's always, you will often find this statement in textbooks. It's straightforward to introduce the spin degrees of freedom. When you read statements like that, be careful because it's never straightforward. It's so easy to make small errors. I actually did that when I made an exercise in a course in quantum field theory. In a textbook, it was written, it's straightforward to solve this problem. So I gave it as an exercise. And it took me the whole weekend to solve it and find the solution. There was a mathematical trick which I wasn't aware of. So never trust, it's straightforward. So I'm going to write this like that. I guess you're familiar with that kind of notation. So this is the quantity we want to calculate, and we want then to optimize this problem. So that means that what we want then is obviously the derivative of d of e. And in principle, this is a partial derivative because we have many of these parameters. But let's now just think of it as one parameter. So this is the quantity which we later are going to calculate. So if we now assume that we just have one value, one theta only, then we can make a plot of the energy as a function of theta. So this is what you will typically get now. So we have one parameter only. So this obviously becomes a two-dimensional plot. So we have theta here. And then the energy is going to look something like this. And this is where we have the optimal parameter theta. So when I write a hat on top of it, this is normally the optimal parameter. So this is the value we want. Now, in the beginning of the project, we are going to do this in a brute force way. So brute force means that we are going to calculate the energy for different theta values. And we then just infer from the I by just looking at the graph where the minimum is. That is a quick and dirty approach. You will be surprised to see how many people actually do this by the eye. And many people do even statistics by the eye. But we have ways to find this minimum, and that's where we are going to use some Newton-based methods to find the derivative of the energy. So you will see then that what we are going to develop a little bit later is actually the derivative of this integral. And that's going to give us a slightly more complicated equation, but that's the equation we will implement numerically. But the first approach we are going to do now is simply to calculate this energy for different values of theta. And the energy is, as far as I've seen throughout my physics applications, is that the energy is always a convex function. Now, the energy which we get may not be the exact one. So you could now think of this being the exact energy. So this is E0. And when you have an ansatz psi of t, so we could call this now psi of t1. So this is our first trial function. Then we could choose another one, and the other one could perhaps go like this, and it could get closer. So this could be a psi of t2, and then you could continue like that, depending on how expensive these calculations are. And then you would normally pick the one which gives you the lowest energy. So let me quickly remind you of the variational theorem, just so that we have everybody on board here. So suppose I have the exact solution to Schrödinger's, or to the equation here. So suppose now that H, this is the Hamiltonian, acting on a basis psi of I, is now given by some eigenvalue times psi of I. And I'm, by just plain sloppiness, I'm skipping the Dirac-Braket notation. I hope you can forgive me here. That's another way of doing that. But we will often skip that because we are going to include all the degrees of freedom, the spatial degrees of freedom, etc. So assume now that this is an orthonormal basis. So psi of I is an ONB. So O, orthonormal, normalized basis. So I don't know if you're familiar with that kind of shorthand. So the basis, when you have an eigenbasis for a problem like this, a differential equation, a linear problem, then you have an orthonormal basis. So O for orthogonal, N for normalized, and B for basis. This basis is in principle infinite. Now, one of the things which we can do then, since we are solving a linear equation, so Schrödinger's equation or Dirac's equation are linear equations in the unknown quantity. And since these are linear equations, we can now expand a new function. And let's call this function for phi. This is now something which we can expand in terms of a set of coefficients. And in principle, this sum goes to infinity. And then we have a set of coefficients, Ci, multiplied with this psi of I. So you can do that classically. The only difference quantum mechanically and classically when you solve a linear equation is that quantum mechanically you can actually have entanglement. This is just a superposition of solutions. And I guess you're familiar with that. And this follows from you solving a linear equation. So you may be familiar with Fourier expansion. That's also an example of a linear expansion in terms of cosines and sines. So when you have a linear equation, you solve that one, you get an orthogonal basis, and that basis can be used to make an expansion or superposition. Now, what we have now is the following. So if I calculate the energy, and this is now the expectation value of the energy with this phi. So what I want now, and now I'm going to introduce this kind of Dirac notation, Dirac-Braket notation. So this is now given by this state multiplied with the Hamiltonian acting on this state phi and divided by the norm. So that means when I plug this in, I'm going to have a double sum, ij, and then I'm going to have the C of I, Cj, complex conjugate. I will have my state psi of I, of H, of psi of J. And then in the bottom here, I will simply now get a sum over the CIs, because this is an orthogonal basis. And then we know that these are eigen states of H. So this is just nothing but the sum over I, and then I have the eigenenergies, E of I, and then I have Ci squared divided by I of Ci squared. Now the denominator is equal to 1, because these are orthogonal basis sets. So this is normalized to 1. So this sum here is something which we normally require to be 1. So this is something which then is equal to E of I of C of I squared. Now, if this phi is an exact solution, suppose that. So suppose now that phi over phi is exactly equal to psi 0, just to give you an example. That means that all the other coefficients are 0. So then what it means is that this expectation value of phi, of H, of phi is actually equal to E0. Because then all the other coefficients C of I are equal to 0. So then the only coefficient C of I, or the only one here, is equal to 1. And all the other ones are 0. If not, if we don't have an exact solution, if you have a mixture of some of the other components, the energy you get will be larger than the exact one. So if that is the case, if not, then this expectation value, if not, then E0, which is the exact result, is going to be larger than this sum here. And this is the variational theorem. So if you have the exact solution, you will get the exact ground state. If not, you will get something which is larger. Okay, so this is an important aspect, and that's why we call it variational Monte Carlo. So that integral we evaluate will provide us always with something which will look like this. And if we happen to have the exact one, as you will see later here, we should be exactly here. Now, how is Monte Carlo done, the variational Monte Carlo done? So if we now look at the expectation value we want in terms of these variables theta, what we are going to calculate is this multi-dimensional integral, d of r. And now I'm going to show you the standard trick which we are going to use in order to calculate this integral. And then divided. You also see now that there is a nasty component here. And this nasty component is the denominator. Because that requires you evaluating something which can be pretty tricky to evaluate. Now, one thing which comes to our rescue here is actually the Metropolis algorithm, which will allow us to avoid evaluating that denominator. But let's look at this quantity. So what we define now, a probability. So probability density function, or just probability. If we now think of quantum mechanical probabilities, that is the wave function squared. Divided by the norm of d of r of psi of t squared. And I'm skipping the r and theta dependence in the denominator. That should be pretty obvious, right? The next thing which I'm doing is now to define a quantity which I'm going to call the local energy. So this quantity is going to be a function of this r and this parameter theta. Now, you can actually show that this quantity here, when the denominator, so it has actually psi of t, of r of theta, multiplied with the Hamiltonian, acting on psi of t of r of theta. This is called the local energy. Okay? So if you look at what we have here, if you look at this term here, the local energy, and also this probability distribution, that allows us now to rewrite Schrödinger's equation in a specific way. So I'm going to give this a name, actually, the probability distribution. So this quantity which you see here is something which I'm going to label as a P of R of theta. So that's the probability of being in a specific position R with the parameters theta. So this is nothing but our standard quantum mechanical definition of a probability. So if I do that, I can now rewrite Schrödinger's equation. By the way, there is a small typo here. I forgot to put that one here. Now there should be a complex conjugation there. Okay, so what I'm going to do now is simply to insert in here, I'm going to insert psi of t divided by psi of t. Then I can rewrite everything in terms of these two new quantities. So my expectation value of the energy is now going to be an integral over R, so which is contained a specific domain here of d of R. I have my probability for this trial wave function, T of E L of R of theta. So how many of you have taken a course in statistics, standard statistics? Okay, so the thing is that an expectation value in statistics is now given. Let me just remind you of that, because what we have here is actually a statistical expectation value. In statistics, in stat, so if I have a variable like, so you would typically, if you go into a textbook in mathematics, you would often see that with this letter here, E, of some x of n. We physicists, we often write it like this. You've probably seen that notation often. And formally, this is now given by x, where d of x, where x now is defined in a specific domain. And then I have my probability, P of x, multiplied with x to the power of n. That is an expectation value. And since we have x to the n, we just call it the moments of x. Okay? So that means that what we have here, if you look at this equation, this is nothing but a standard statistical expectation value. Now, our problem then is that we are going to evaluate this with Monte Carlo sampling. So let's rewrite this integral which we have here. So this one is now going to be approximated. This is the way we are going to do that, with 1 over the number of Monte Carlo cycles, MCS. Now let's just call it M. Let me just call it M here. That's much better. So this is the number of M, is the number of Monte Carlo cycles. Or Monte Carlo samples, Monte Carlo suggestions. So you will see that I'm going to use many names. So Monte Carlo sample is one of them. I call it sometimes cycle because that's just one element of a loop of all the possibilities which we have. And this is going to be a sum from m equal 1 up to I equals 1 up to m. And then we are going to calculate this expectation value in terms of these different samples, Ri, as a function of theta. So what we are doing now is to invoke something which is called Bernoulli's law of large numbers, which is so that if m is actually going to a huge number to go close towards infinity, we are getting something which is approaching more and more the exact expectation value. So the quantity which we will evaluate numerically is this quantity here. So we are going to suggest positions Ri, and we are going to suggest as many as possible. So with that, we can then estimate this integral. And what we are going to look after then is whether this expectation value converges to a stable value as a function of m. So if we have few samples, this will oscillate from observation to observation, but after some time, this is going to stabilize around a mean value with a specific standard deviation. So I'm giving now you the overarching things so that you can see how we are going to implement this numerically now. Okay? So the last part we're going to do today is to look at our first Monte Carlo code. So I'm just going to give you the way of doing that as a code. But then next week, we are starting to dissect all the steps which we have taken here. In particular, we're going to develop the Metropolis algorithm. We're going to look at the mathematics of Markov chains so that we can understand how we actually reached this specific equation which you see here, and why this is the one which for all practical purposes we are going to use. So this follows from Bernoulli's law of large numbers. So in principle, what we have done is to replace the probability here with a uniform distribution. That's essentially what we've done. So every event then is equally likely. But let's now go back to the Jupyter notebook and look at how we can implement this. So let's just do that and take the full screen, this, and then we go back to the Jupyter notebook, and we are going to take a closer look at how we would implement this. So what we did now was simply to set up the expressions. This is what we have here, except that I use m in the lectures and in the notes and alpha. So the quantum Monte Carlo algorithm runs as follows. This is essentially what you would have to include. So you need to fix the number of Monte Carlo steps or cycles. So this number n is something you need to decide upon. And you will typically see that the results get better and better the more samples you can plug in. So because then you get a more representative sample. And you can understand that if you think of calculating an integral with a statistical distribution, and then if you have few points, then clearly your integral is not going to be well valued. If you have many points, you will get closer and closer to a good expression, and in some cases, the analytical expression for the integral. So what we are going to do now is to implement a very simple approach, which often is called brute force Monte Carlo, or just plain Monte Carlo. And what we do now is that we fix the number of Monte Carlo steps, we choose an initial position for the particles, and we have a set of parameters alpha. These are the parameters we want to vary. I call them theta in the notes here. And then I initialize the energy and the variance. So let me quickly remind you of the variance. So in case you may have forgotten some of these things from statistics. So let's just do that. So the variance is an important quantity. So let me remind you of that. So if we go back to this variable x, so the variance of this variable x is now written, if we have a continuous distribution, we have d of x, we have the probability p of x, and then we have x squared, or x minus the mean value. This is the expectation value of x, e of x squared. And we would typically write this as the expectation value of x squared minus And then this is the expectation value, the mean value of x, like this, squared. So this is the mean value squared. So quantum mechanically, what we need to do then is to calculate the expectation value of the Hamiltonian square. So the quantum mechanical variant, Qm, is actually you calculating d, and now I'm just looking at a one-dimensional problem. So I have a psi of x, and then I have the Hamiltonian squared times psi of x divided by the norm. So I have a d of x psi squared minus the expectation value squared, or the mean value. And now I'm getting a little bit sloppy with all the x dependencies. And this is squared. Now, can you see what the value should be if you have the exact wave function? If you look at the quantum mechanical expectation value or the variance, so this is the quantum mechanical variance. This is what you would typically see in any textbook in statistics as a definition of the variance. Quantum mechanically, it's actually the Hamiltonian acting on the wave function. So if you have the exact solution, then you have E of psi is equal to E times psi here. So if you plug in, if somebody gives you the exact solution, what should the quantum mechanical variance be? If you look at that expression. So before we got, I am a soccer idiot, a football idiot, what you might call. And before we had Haaland, Ødegaard, and so on, Norway had a number of points which they always achieved in any qualification for the World Cup and European Championship. Never got any points. So this value here, if you have the exact function, is equal to the number of points Norway would get in any football qualifications before Haaland and Ødegaard. Yeah, 0, exactly. So you have a measure here. We don't have the exact function. So that means that our variance will not be 0. So when you're being asked which wave function, if I were to give you 2 wave functions, you would obviously pick the one with the lowest energy, but you would also pick the one which has the lowest variance. So that's a typical measure. You will see often that lower energy means also lower variance. But in this case, you have an exact value if you have the exact function. So you have something you can look after. So when people do the optimization often, they calculate both the variance, they optimize both the variance and the energy. But this has been dropped because calculating the expectation value of the variance numerically means having to evaluate 7 integrals. As you will see later, the derivative of the energy involves only 3 new integrals. But let's go back to the algorithm then and just show a demonstration of the Monte Carlo algorithm, which we will discuss in more detail a little bit later next week. So what we do then, this is essentially the algorithm. You initialize, you choose an initial position, you calculate the initial energy, and then you find a new trial position. And normally what you do then, you take the previous one, you find a random number between 0 and 1, and you multiply that with a step. So this is a brute force way. It means that the way you jump in space is something you decide. So if you then go back, and you will see quickly that what the problem is. So let me go back to the simple case. So let's switch back to the whiteboard again. So suppose now you want to integrate this function here. And you will see from this algorithm here that if I am here, so this is x0, my initial position. If I make a large step, so this is the function I want to integrate, f of x. So I want this expectation value, and there may be a probability, p of x, v of x. Now, if I make a big step, you see now that then I may enter a region where this function is 0. So if I make 2 large steps, and suppose I make a new step where I end up here, for instance, then you see that my function here, and in this point here, is 0. So if I make 2 large steps, I will be accumulating zeros. And that means since I'm calculating the integral in this specific way, so this is the way I'm calculating it, of x of I here, it means I will have lots of zeros. If I make it too small, on the other hand, then I will just be jumping a little bit back and forth here. And then you will also not have a representative or a good representation of the function itself. So this kind of step which you're setting up is something you often tune so that you can cover the whole function where it is non-zero. This is normally called a brute force way because you're not guiding, you're jumping according to the probability of being in a position in space. So the standard metropolis algorithm, as we will implement first, needs us tuning this step so that we sample points which are non-zero, or that we also don't end up staying in the same point or close to the same point. You see the basics here? When you do the sampling, you need a representative set of points. So let's just go back to the Jupyter notebook then. So we would choose fine-tune this one, and we would then afterwards, and this is something which we haven't derived, we will use the metropolis algorithm to accept or reject the move. So we look at the probability in the new state divided by the probability in the previous state. So that's why we need this probability. This is the metropolis algorithm. And we accept it if we pick a random number so that this is larger than 1. And then if the step is accepted, we set the new position to that one. Else, we just stay in the same position. So staying in the same position, not moving, is also an observation. And then we update the averages. Now, there is an example with the hydrogen atom, but I wanted to show you the, before we move on here, because there's also an example on the harmonic oscillator, which I wanted to bring up here. So the harmonic oscillator, this is the function which we will start with. So the first part of the project needs you setting up the trial wave function for the harmonic oscillator. So this is one particle in 1 dimension. If you have 2 dimensions, you have x squared plus y squared. This is the ground state. So what I did here was to put h bar equal to 1. These are normally called natural units. And then I put my omega here. You can put it to 1 if you want to. But in principle, this omega is baked into this constant alpha. So alpha is my variational parameter. So this is the parameter now which I will vary when I calculate the energy. So when I take the derivative, when I go back and calculate this local energy, so you have this function, I take the harmonic oscillator, which has a very simple Hamiltonian. It has this part plus x squared. So if we go back then, so you can see the harmonic oscillator has something like this for the potential. In the project, we're going to implement this part first. So if you go back and calculate the local energy, the only thing we need to do then for the local energy is to have 1 divided by the wave function, the Hamiltonian with the kinetic energy part acting on this one, plus the potential energy part. So we need to evaluate this function here, which is a local energy. And that means mathematically that when I do that, I get this as a local energy. And then I'm going to integrate this up. And then I have a mathematical analytical expression for the energy. I can also calculate the variance, which is this one. So this function here, this one, gives the exact energy if alpha is equal to 1. And you will see that in the code which follows now. So this is just a beginning setting up directors and so on. Here, I define my wave function. So it receives the position R. and this parameter alpha, which is now my variational parameter. And it returns also the local energy. So what I did here was actually to punch in that expression. So these are things you can object orient if you want to. And then what I do here, I set up 100,000 Monte Carlo cycles, the step size to 1. I initialize the old and the new positions. I do my variational parameters from 0.4 in steps of 0.05. So I calculate, I think, 10 of these so that I can actually hit 1 where I have the minimum. So I'm doing a calculation by the eye now. I just calculate for alphas. I can do that here because the harmonic oscillator is so simple. So I loop over the variational parameters, no, the variations. I do my Monte Carlo cycles, which you see here. I've chosen 100,000. If I choose more, I will get a better result, and you will see that when you play around. So feel free to play around with these parameters, and you will see how much they will change the results. And then I do the new position, which is just the old, plus this step. I have minus 0.5 because I want to have negative x and positive x values. Then I calculate the new wave function. I do the metropolis test. I pick a random number between 0 and 1 and compare that to the new wave function squared divided by the old one. So we are coming back to this next week in more detail. Now I calculate my contribution to the energy and I update the energies. So every time I calculate a new local energy when I have a new position, I can stay in the same place or I move to a new place. Then I divide everything by the number of Monte Carlo cycles. I do the same with the energy squared, and I do the same with the variance. And then I print. So let's just rerun the code here. I just need to rerun everything from start. So let's run this. And now you will see a typical example of, so I do 20 variations. I calculate the energies. I compare with the exact result because this has analytical solutions. And this is why this is so useful when you're building up your project. So in the beginning, I want you to test this for 1, 2, and 100 particles, which are not interacting. So if you have 100 particles in one dimensions, this is just this energy for one particle times 100. So that's a very easy test. So I plot now, and what you will see then is something like this. So this is the energy. And you see now it has its minimum, as I said, it's actually at alpha. Alpha is 0.5 in these units, and it has a minimum at 1. This is the exact result. So the blue ones are the exact ones. If I look at the variance, you see now that at the minimum here, the variance is exactly equal to 0. So that follows what we expected. If I have the exact wave function, the quantum mechanical variance is exactly equal to 0. And now you see, if you look at the numbers, if you look at these, you will see that numerically, so this is done numerically with a Monte Carlo code. And you see now that you're basically spot on, 0.5, which is the exact energy, and you have a variance, which is 0. And then you see the theoretical one. Now let me just reload this one, stamp page. If you see now the variance here is starting to differ a little bit. You see the energy is not that different. If I now increase, you see here it's 2.78, and this is the exact one. The exact energy is also a little bit different. So it varies at the third number after the decimal point. But if I now increase, and this is the last thing we will do before we stop today. So if I increase the number of Monte Carlo cycles and I rerun, so let's do that. Now I have to actually have it. It wanted me to leave the page, so let me just rerun everything. And this will be the last thing we do in the lecture today. Now it's going to take a little bit more time because I went from 100,000 to 1,000,000. So you see, the accuracy you're looking after will depend on the number of cycles you're willing to spend. So if you now look at the difference between these numbers, so let's just scroll down, you will see now that they are closer. So I increased the number of Monte Carlo cycles, and I got a result which now agrees for left for the energy at the fourth digit after the decimal point. The variance is getting closer, but it still varies a little bit more because now you're evaluating two integrals and you're taking the difference between two integrals. And each integral is evaluated stochastically. So clearly then, when you do two integrals and you subtract them, you're much more sensitive to the exactness of each integral. But you see, this is essentially what we are going to do in the first project. We are going to build up a code where we do 1, 2, many particles. And we are going to do this in 2 and 3 dimensions. But we start in 1 dimension. So you starting to build up a code like this example is what we want you to start with. And we have these templates you can look at. So when we go up to the lab now, if you have time today, this is what we can discuss after a small break. And this is where we'll stop. So I wanted to give you the kind of overarching view of where we are going. And then we need to fill in the different mathematical details. So the metropolis sampling, we're going to look at Markov chains, how do we derive the metropolis algorithm, what does it mean, and all the small things which we need in order to get a code, which at the end is going to look like a professional code for doing Monte Carlo calculation. So our end goal is going to be a professional code for doing the calculations. That sound like a okay goal? Okay, I'm going to stop here now. So I'll stop the recording.